investigation, we have a traditional approach, which based on the work at the laboratory in using different materials from periodic elements, and we have the new one that is based on data science or data mining, which using calculations are made before, and combine it with artificial intelligence using informatics, for example, codes to create new materials. Our used tools, we all know the Hamiltonian of in Schrödinger's equations. It's a collaboration of kinetic energy of nucleus, electron, and potentials of electron-electron and electron-nucleus and nucleus-nucleus. And the DFT is allowed us to move from function waves to three from 3n variables to 3 variables, density variables. We have x, y, and z. So the motivations, the first motivations are, as we see, the numbered applied of fields. We have, for example, phototherapies of cancer cells. We have bioimaging, catalysis, and biosensors. The second motivations are the developing of IT tools and software. We allowed us to push our hope of creating or developing new materials. For example, the advanced supercalculators and the software like Quantum Espresso, VASP, Siesta, and so many others. For the third motivations is creating databases. After doing, for example, research using the DFT approach, for example, we will collect important data, and we making it together. We can use it when they are necessary. For the fourth motivation, we have the economization of cost and time. Like we see before, we have the ancient approach to create new materials is that we use the materials at the laboratory to make it, to try to make it, to make new nanomaterials, for example. But if we use, for example, data mining, we can economize cost and time. For the research items, we choose the 3 materials, which the germanium was the base, the cage of. We used clusters of germanium, which by institution 1 atom of germanium by palladium and platinum elements. For the processing, we have for the first demarche we have to generate different isomer structure. For example, you can do it by freehand or using genetic algorithm. After finishing the first process, we make structural optimization. In our case, we use the conjugate gradient algorithm, which is implemented in Siesta code. For the electronic optimization, for example, to have bending energy, homolimo gap, VIP, and so others, we carried out using code Siesta code package. Is open source package. For sticking result, after doing these three steps, we have data. This data we need to try to figure of them the good information for searching for most, for example, searching for the most stable isomers between all isomers we done before. For the last one, creating small database, collecting the final hypothesis and on every clusters or treated materials. For example, when we finish a study, we try to collect them on a small database to be used after that. For example, on my research or my calculation, I tried to figure out germanium clusters by doping or substituting one germanium atom by, for example, this one is a platinum atom. And the second part, we use to substitute one germanium atoms by a palladium one. And we see that for the smallest clusters, we have a flat, for example, structure here. And moving on cluster size, on augmentation on cluster size, we have 3D or cage-like structure. And it's the same thing for the palladium germanium clusters. For the electronic properties, we carried out here bending energy. We have, for example, as we see, the red one and the green one was germanium and germanium, palladium, and germanium platinum clusters. When the black is pure germanium clusters. For example, bending energy, gain of energy during the growth process. We done the down and homolumo gap, or the gap total here, for the three elements. For example, for the total gap, we have a semi-metal behavior. We see that it's overlapping, but for the most of them have a semi-metal behavior. For the VIP, vertical ionization potential, we have a decreases of ionization potential by increasing the cluster's size for the third element, or for the third cluster studied. And for the electronic affinity here, electronic affinity, vertical electronic affinity, we have an increasing tendency or with the oscillation character after. For the chemical hardness here, we have a decrease in process, environmental interaction. We carried out that the clusters have a tendency of interacting with environmental, exterior environmental. Some
excuse me,
value of
2 minutes.
For table corresponding stable isomers, bending energy, VIP and VR, so the gap total, hardness, chemical hardness, for the clusters which 2 atoms until 21 atoms. It's for palladium and for the platinum. Conclusion, we see that the platinum and the palladium atom is located in periphery for all the structure under 10 atoms and for 9 atoms respectively. When the N atoms is upper to 10 and upper to 9 respectively for palladium and platinum and palladium, the doping atom is encapsulated in germanium cage-like, The stability of the germanium framework is affected by substituting one of the transition atoms, as we see on the bending energy graph. A near metallic behavior for stable isomers was observed for all the clusters. And thanks for your attention.
Merci.